Read the following questions and pause the video and attempt these two questions. Let's look at part A. For a metal foil with n layers of atoms, explain why the probability of an alpha particle being deflected, and when we say deflected, it means by more than 90 degrees, by a given atom is about 1 in 10,000 n. Now, importantly, it's by a given atom, and I'll explain why that's important in a second. So let's simplify it for a second. Let's look at a single alpha particle being fired towards a sheet of atoms with only 5 in it. So what's the probability that it's deflected by a given atom? And what I mean by that is this one here. Well, the probability is obviously 1 out of 5. Now, if I, instead of having 5, if I have n atoms, what is the probability? The probability is going to be 1 over n. Supposing now I don't have one layer, but I have more than one layer. Let's look at something that's got 3 layers just to keep it nice and simple. So now, what is the probability that's deflected by this atom? And it's by the given atom, not any atom, but this one here. Well, the probability is going to be 1 over 5, but it could have been deflected by this one, it could have been deflected by this one, it could have been deflected by this one, and we only care about it being deflected by this one. That's the given atom. So it's 1 over 5 times 3 to represent the fact that we've got 3 layers. In general, it's going to be 1 over n for the number of atoms times by the number of layers. Now, importantly, the question tells us that about 1 in 10,000 alpha particles incident on a thin metal sheet are reflected by more than 90 degrees. So what we're really saying is the probability of it being deflected if there was one layer is 1 in 10,000, but there are multiple layers, so the probability of it being deflected by this given atom is 1 over 10,000 n, or simply saying 1 over the total number of atoms. So part B, it says, assuming this probability, so the probability 1 over 10,000 n, is equal to the ratio of the cross-sectional area of the nucleus to that of the atom, estimate the diameter of the nucleus for atoms of diameter 0.5 nanometers in a metal foil of thickness 10 micrometers. So this probability is equal to the ratio of the two areas. So I'm going to redraw my simple diagram here. And again, this is the given atom. This has diameter D and it has area A, and the whole thing has diameter D and area A. So importantly, what is the area? Well, the atom we're modeling as circular, so it's 1/4 pi d squared, and of course it's not one line of atoms, it's actually a square, or maybe we can model it as a circle. So the area would be pi, so 1 over 4 pi d4, because if you imagine the alpha particle going head on, it's going to be confronted with a sheet like this. So we're going to model the overall area as this. So the ratio of the two areas is pi, so 1/4 pi little d squared over 1/4 pi big D squared. Obviously, this cancels with this, so we're left with our expression here. So we want to find the diameter of the atom, so we rearrange like this. Now, we've been given the diameter in the question. The diameter was 0.5 nanometers, so 0.5 times 10 to the minus 9 squared. And how many layers are there? Well, if it's thickness 10 micrometers and the diameter of one atom is 0.5 nanometers, then we can say that the number of layers is 10 micrometers over 0.5 nanometers, which is 10 times 10 to the minus 6 over 0.5 times 10 to the minus 9, which equals 20,000. So this is going to be over 10,000 times 20,000. And then we obviously need to square root all of this to get our diameter. So let's plug all that into our calculator. And we see we've got 3.5 times 10 to the minus 14 meters, which is approximately what we would expect. Now, the typical values that we're expected to remember for an atom, we're expected to remember the typical diameter of an atom is 10 to the minus 10 meters, and the typical diameter of the nucleus is 10 to the minus 15 meters. This is close enough to that to be confident that we are probably correct. Interestingly, this has a name as a unit. This is called an angstrom because it's a very convenient method of measurement. However, this is not something that we need to use in A-level physics. This is something that comes up more in chemistry.